Hello, everyone. Welcome back to CPE 517-WS Digital and Computer System Architecture. This is the last part of lecture 6 about page fault and the exercise for address translation. So what is page fault? Page fault means when a process references a page, this page is marked invalid in the page table, which means this page is not actually in the page. In the memory, sorry. So in that sense, we're gonna have a page fault, like this page is a fault, right? So it's gonna be trapped by the operating system. Then the operating system will find a free memory frame and read the desired page from the disk. So this is very important. It's not in the page, does not necessarily mean it's a segmentation fault. It's a page fault. For those of you who knows what is segmentation fault, it means your access is illegal, right? When it is a page fault, it means your access is legal, but the page you're accessing is not in memory, okay? Where it is? It is in disk. It's swapped out, like what we mentioned earlier in virtual memory. We know that virtual memory does not really put all those required memories in physical memory. Some of them are actually swapped out in disk. So what we're gonna do is we're gonna check whether the reference is valid. And then we find a free memory frame, read desired page from a disk, change valid bit of page to valid, restart instruction that was interrupted by the trap. So basically what we do is like this, right? Okay, so assuming we're executing, then it triggers operating system. And then this operating system gonna load the page from disk to memory. Mark the valid bit of the page to valid. And then let the program execute again, okay? This is called context switch. And then we're gonna restart the instruction again. Like what we restart instruction gonna do is we're gonna restart the 5-stage pipeline, instruction fetch, instruction coding. If there's no free frame, what are we gonna do? I think this is something we learned before. So we will free the least recently used page. Like that one gonna be swapped from, not free, swapped from the main memory to disk, and then this frame is free, right? Then we're gonna load the desired content to this specific page and create a virtual address and a physical address binding to this one. The cost of the page fault is a lot. It is typically set in the time of seconds, right? So page fault actually degrades the performance by this many times. You have to basically seek the disk, access the memory. Yeah, this is like a 100,000 times. So it's definitely better not to have too many page faults. If you want no more than 10% degradation, you can only have one page fault for 1 million instruction, 1 million memory access. So this requires the operating system to do a better job swapping data between and the secondary storage and the main memory. Okay, can you guys use 30 minutes to do this address translation? It's gonna show in your exam, okay? For virtual address of 64 bits here. 64 or 64. The page size in the virtual memory is 16 kilobytes. That is how many, right? How many bits for this? L1 cache is direct map 16 kilobytes. Okay, 16 kilobytes. So what's the index, right? And the block size is 64 bytes. This goes here. And also here. This together tells you this two-way set associative 128. 128 sets. Since the physical address is 40 bits, so you can figure out this. Because this plus the page offset is the physical of 40, right? And that's it. Please pause the video for 30 minutes and solve this problem. Okay, welcome back. This is the solution. 60 virtual address 64, physical address 40. Since it's 2 to 14 equals 16. Okay, bytes. Since it is you have in total 16 kilobytes and then 64 bytes. So it's 2 to 16, 2 to 14 divided by 2 to 8. Sorry, 2 to 6. That's why you have that 8. Because in total you have 256 block entries. And then the block size is 64, so it's 2 to 6. Right? This is also 2 to 6. Since this is page offset is 14, then L1 tag is 26 because together they go to 40. Since this is 26, then this is also 26 because it's the same. And then, because this is 50 in total bits, and you have in total 128 sets. This is 128 equals 227, right? So then we have 50 minus subtract 7 is 43. 43 is here. You have to compare. Then we finished all of them. Top. L1 tag is here. We compare. And then L2 cache, you have in total 4 megabytes. 4 mega is what? 2 to 22. Divided by 4 ways, 2 to 2. Divided by 64 is 2 to 6. This goes to 2 to 14. It's to the 14. And then 40 subtract 14 and 6 goes to 20. 20 is the 10. Please let me know if you have any questions. All of them are like a binary to address translation. Okay, this is also the explanation about it. Right. That's it for lecture 6. Thank you.